Hey, hi everyone. Thanks for joining this talk. I'm Irina Vidal. I'm really happy to be joining PyData Global 2020. And today I would like to talk to you about how to proceed when you want to generate more visual data. Simulating, boosting, augmenting, generating data is definitely not something specific to computer vision, but that's the approach that we're going to take today. Now, this particular problem is even worse for vision, considering that we're at an age where everything is full of cameras. So there is a lot of surveillance going on. We know that, which at least the only bright side of it could be that once you want to access that data to do something good about it, it should be easy, right? It should be, you should have plenty of different of images, of videos to train any kind of use case, considering that there's cameras for all sorts of applications, from industrial to surveillance to security, to multiple sensors on vehicles, in medical diagnostics, and everywhere, basically. However, accessing that data is a completely different story. It exists, it's sitting, plenty of times it's sitting somewhere, but whether it be for very good reasons like data privacy, or for simple, or for actually technical reasons, or because that amount of data is not annotated, and we know it's extremely expensive in the end to properly annotate your data, or maybe you do have annotations, but they match a completely different use case, or perhaps your use case at this time requires a completely different sensor, which has a different geometry to what you were expecting. Whichever the case, plenty of times, once someone gives you data, even if you get access to it, it's not something you can use immediately. And so, of course, this is not a new problem. This has been going on for ages, and it's not particular to deep learning or neural networks. It just is a bigger problem now. Now, there are plenty of workarounds that we've all used, right? So, of course, transfer learning is the first thing you go to. There's plenty of open data sets, and at least that can give you a head start. There's also 0, 1, few shot learning to try to work with very little data. But something also very intuitive is to think, well, maybe I can simulate my own. Maybe there is something that I can create, or at least that I can do to multiply the little data that I have. And that's what we're going to be looking at today. Now, let me share with you the assumptions I'm making and a bit about me, so that we're all on the same page. So I'm one of those people who has suffered for lack of data. And I typically work on the machine learning and or computer vision side of products. For the past 10 years, it's been a mix of startups and bigger corporates, from mostly medtech, but then a bit of entertainment and e-commerce startups, and more recently, mobility. Now, what I'm assuming about you is that you have perhaps a similar profile, as in you're interested or at least familiar with machine learning or perhaps computer vision, that you've also suffered the lack of data. Perhaps it's the same pain points I have sometimes, and that you're tempted to generate your own. And you're curious to know how to proceed, what tools are out there. And that's exactly what this talk is going to be about. What tools there are, where they fit, where they can help, where maybe they can't help that much. And the way I'm structuring it is, of course, it cannot be super comprehensive. However, these are several tools that I've found fairly useful. And the way I'm going to present them today is I found it a good approach to structure them, to structure the approaches that I take towards problems. So I'm going to be talking about these techniques that you're seeing around here, and also think about them from the perspective of these purposes. So at all times, I'm going to be thinking and sharing with you, could these fit in a training setting, in a testing setting, or perhaps as anonymization? Right. One other thought, all of these, in my point of view, can be somehow put on a spectrum between how close they are to the original real data, to the unreal, virtual, completely synthetic, and artificial domain, which would be about here. And we'll see in a minute why. So let's start with augmentations. In this case, I'm lumping together classical augmentations. So the easiest thing that you can do is perhaps play around with the intensity of your images, the contrast, perhaps saturation, and the like. Then another completely different family of augmentations are adversarial. And I'm going to lump them in here because at their core, they are adding something to real data. So you're starting off with real examples, and you're doing something to them. You're adding, for many of the methods, you're adding perhaps some artifacts, which are not noise. They are targeted, they have an intention, and they have a method to them. But in the end, it's adding something to real data. And in a way, you're creating more samples similar to those initial ones you had to generate more data that you can use either in training, testing. We'll see about that in a bit. Now, there are quite a few open source tools that you could start using. You don't need to go at it alone. But one thing you do need to think about is, of course, tools like Pillow or OpenCV, they can take any image and you can do all sorts of things to that image. But one thing you need to remember is that typically, if you're within a machine learning problem, unless it's an unsupervised problem, you're going to need annotations, right? At some point, you're playing around with bounding boxes or with the outlines, with polygons around the objects or the creatures that you're interested in. And so one thing that these tools can do for you is at the same time that you're augmenting and maybe rotating, resizing, or applying fine transformations to your images, what they'll do is apply the necessary transformations to those annotations as well. I'm listing here a couple of tools that I encourage you to look into. Of course, you can use them. They've got a Python API. And of course, if you don't want to, you can always write your own using the usual culprits. Now, moving on to the adversarial one. So typically, we've talked about adversarial attacks in the past, even at PyData. This here is the most basic attack. I would say I think it was probably the first one published. If you want, since this is the video, you can always pause it and go look for the fast gradient method. What you will see is at its most basic, this is about from a model that you know or that you suspect what it is. You generate. This is not exactly noise. You generate an artifact that you can then overlay over your initial image, and that results in a second image that is an adversarial example. And that ideally, even if your initial image was very clearly identified as something like a laptop, once you've added that apparent noise, it will be misclassified as something else. And you'll find that this does not only apply to classification, this applies to many other use cases, but let's not dwell on that right now. All I wanted to share with you today is that there are as well several toolboxes that you can use, and it could make sense to use them at least during your training step. Why? Because just like you do with classical augmentations, you're going to want to have your vanilla training data, but you also want to generate plenty more of those that are slightly different, that are more challenging to the model so that it gets used to extracting, to learning what features are really important to specific classes, right? And so this setting could easily look this way, where you have your vanilla training data, you start taking out different augmentations from whichever toolbox you've chosen, and you end up having the original data plus many, many more training samples that you can then use to train your model. Now, it's up for discussion whether it makes sense to use classical augmentations at testing time. Personally, I prefer to stay as close as possible to the real data that you're going to be using, where perhaps your augmentations could be adding some biases. But definitely for adversarial examples, for adversarial augmentations, so to speak, it does make sense to add them to your testing set, because it stands to reason that, well, it pays to be paranoid, right? Of course, this depends on how exposed you think your product or your company is going to be to such a fact, but it doesn't hurt. Well, it could hurt depending on there is literature describing how this might hurt accuracy and so on. However, we can assume for the time being that it doesn't hurt that much to be paranoid and to try to train your model to be robust to these kind of adversarial attacks. So what you can do is, once you've already trained your model, so let's assume you had your training data, you obtained that data, we don't know how, right? But you've used it, you've got it trained, and now it comes the time to actually test it. And what you would probably want to do is be able to know how ready you are to adversarial attacks. So what you can do is, just like before, you get your adversarial toolbox, you have a hands or whatever, and you start applying those attacks to your testing data so that in the end you have a boosted or an augmented data set, including those attacks. And of course, once you test, you're able to say, well, I'm robust against attack X and Y, but I'm failing at Z with this kind of percentage. Now, so recapping this a bit, where does this make sense? At training time, it definitely makes sense to generate those examples that are very, very close to real data. So that's why on that spectrum that I was talking about at the beginning, these would be very close to the real side. However, with specific distortions to help your model learn better features. And then when you start thinking about adversarial attacks, it makes sense to apply these toolboxes, these tools to both training and testing data sets. And now a note on anonymization, blurring, pixelating, cropping out regions. These are all typical transformations, typical augmentations, right? And these can also be used to, for instance, erase people's faces. In fact, it's a really usual tool that is being used to anonymize data, to anonymize videos and images. So these kind of augmentations also make sense in the context of anonymization. All right, just a last note. You should think about what kind of augmentations you're going to be applying, right? So if we think about a toy data set, think about MNIST. What effect would rotating and flipping have on numbers like 6, 9, 2, 5? So it stands to reason that you need to take a look at what kind of data set you have. If you're dealing with classes, will certain augmentations hurt exactly what you're trying to learn? And this doesn't only apply to toy data sets, right? In the case of graphic signals, think that whenever there's arrows, you are going to very much care whether a signal is flipped or not. Okay, so moving on to generative models. There are plenty. Today I'm going to be focusing on GANs and a couple of families of autoencoders, specifically sparse and variational. And these, I've placed them kind of in the middle of between real and artificial, mostly because at their core, again, this could be a good time to pause the video and for instance, if you're not familiar already with them, just check for how GANs work and how autoencoders, specifically variational and sparse, work. But regardless of whether you're training a generator in an adversarial manner, at its core, what it's doing is you first have to give it a ton of data of the kind that you want to create more of. So the model learns what that kind of data looks like. And then at the second step, once it's learned, it'll be ready to create new samples that look very similar to those that it learned before. So in a way, it is generating new data, but ideally, it should be extremely close to that distribution that it learned at the beginning. Now, I'm just going to give you a couple of examples. One of these use cases can be to simulate environmental conditions. So some very impressive results came out of certain papers. I'm listing them here. And if you want to play around, there's also repos where you can play around with these. And these impressive results, as I was saying, dealt with, for instance, translating between summer and winter, day and night, maybe sunny weather and rain. And it can be extremely easy, not extremely easy, extremely useful to, for instance, when you're at the time of training, when you have perhaps only data that pertains to a specific time of the year or a specific time of the day, to have the exact same scenario, but with different environmental conditions. This is not exactly new, so you can see the dates of these papers, but it can be extremely useful still. Now, another application of these kind of models is in face generations. And you can imagine now that here anonymization is a really immediate use case that comes to mind, right? Now, these two papers, this image right here comes from Deep Privacy. This one I generated, of course, this is not the real, this is the real Jan LeCun, but of course, he was not sharing video time with me at all. You can find, so this came from code and a model already trained from this paper, the first order motion model for image animation. And basically, again, these models, so they work differently, but again, they start from real images, and in one case, they are generating a face that does not exist, but that somehow recreates features that existed in the original data. And in this second case, what it's doing is applying specific motion vectors to a face which is real. So this was originally a real photograph. What is not real is that this person was doing these exact movements. It didn't have Jan LeCun following the movements that I was doing, right? Now I'm listing here a couple of repos that you might be interested in trying out as well. One thing I would like to point out is these methods, here you really need to think about why you want to generate your data and what you're going to be using it for. Mostly because you will notice that there are mistakes, right? So this is not a mature technology. There's nothing wrong with that. It can already be extremely useful for certain applications. But if we're thinking about generating training data or testing data, you need to be aware of its current limitations. So consider that, for instance, you can tell that this model has seen an initial data set where there were people with glasses, right? And if you pay close attention, you'll see how since every frame is generated independently, some of those frames show glasses, whereas others don't. So there are inconsistencies. For many use cases, this won't be a problem. For others, it could. So again, as with augmentations, you just have to pause and think, okay, what am I going to be doing with this data? Do I care about textures? Do I care that there are inconsistencies between frames? Do I care that perhaps at the borders, if you zoom in, you would see. In fact, it's quite apparent even if you don't zoom in. There are certain blurred parts. There are some artifacts that are noticeable, and you can see it in the Anacon's face here. You can definitely see it. See where I try to find the limits of it, looking left, looking right. You can see that the model isn't quite ready for those extreme movements. But perhaps for your particular use case, that is not a problem. Right. So I was already mentioning some of these issues. By the way, one of the most successful paper sagas or technology sagas lately has been StyleGANs from NVIDIA. And one of the best applications is to generate more samples of specific objects seen at training time. So, for instance, cars, for instance, faces trained on the celebrity data set. And the limitations that this approach has, in any case, is that you still need data. So if you think about it, we started, the beginning of this talk, we started with the problem that we don't have data. Well, if your problem was that you didn't have annotations, then these kind of techniques can help you. Where they won't help you is to generate that initial data set, because you're still going to, unless you're dealing with faces and you can use an open data set, you're going to need that initial data to train your generative model. The second limitation is that they tend to need those objects to be perfectly aligned. And you can actually see it. And by the way, the images that they produce tend to be fairly small. So they tend to be, so this is the most typical, this is going to be more frequent than big scenes, big complex scenes. This is improving, and every time there's a new StyleGAN, the resolution has improved. But you can still, of course, see these artifacts. And in this image, you can see how perfect the main object is, whereas the car sitting beside it shows some artifact that any human would notice are just, they're just weird. Same thing happens with these kind of faces. And in fact, if you go to, there's this website called This Person Does Not Exist. All of those images, all of those faces come from the papers from this group at NVIDIA. You will see that every once in a while you get one of these faces with artifacts, and in fact it's a bit nightmarish. It's actually fun, so you should take a look. Right. Other problems that you might find is feature disentanglement. I wanted to point this out. So because this is also a point where you need to spend some effort. Other than filtering out failures like this one, there's a problem that has been worked on recently, and it's quite improved. And it's about when you're generating these new images, are you able to say, generate a similar image to what you saw at training time, a face like this one, but I want a different hair color, or I want this new person to have glasses or a mustache or whatever. And that is extremely tricky. Recently, there's been a lot of advancements. And specifically, again, this group from NVIDIA has been publishing a lot. And you can see some applications, for instance, in things like, I want the same person with bangs or wavy hair or going bald. And if you think about it, this requires some control over how the features are represented in latent space, being able to somehow tap into a specific feature in latent space, so that when it goes back to image space, the feature that you wanted is the one that's been sampled and that's been used to recreate this image. So again, the most immediate use case here is actually for privacy and anonymization. So deepfakes have had really, really bad press and they are a danger. It's better that we all are aware that they exist, so that we can doubt whenever we receive certain videos. Just pause and think whether they might be fake. But there is a bright side to them, and that's they have huge potential to enable people to tap into data that they otherwise should not be allowed to touch. So in the space of anonymization, there's a huge potential. And of course, once you consider the caveats that I was talking about, filtering out failures or whether certain features that are reproduced could potentially harm your training data. If once you've established that those don't matter that much for your particular use case, generative models can help a lot in terms of creating more testing data. Now, to finish, I would like to touch the most artificial / synthetic / virtual data that you can generate. When we talk about simulation, we typically talk about game engines that are now used also to create worlds where you can test systems. So there's a Carla challenge that you can see results of. And these kind of tools are very useful if, for instance, you're trying to test a full system that maybe is trying to learn how to drive. So maybe you have a reinforcement learning system that has to learn whether to turn left, right, accelerate, brake, and for that, being able to create maps and create situations with other agents that could collide, those are extremely useful. And as you can see, the realism is fairly nice. It's not sensor perfect, but it looks really good. And they don't only give you RGB data; they can only give you modalities as well. So examples of this are, as I was saying, Carla. You also have AirSim, but there's a list of simulators that you can use. Some of them are based on a real engine. Some of them are Unity based. And what I would like to point out here is that, as I was saying, if what you're trying to test it's a full system that is trying to learn how to operate in one of these worlds, these simulators can be extremely useful. But again, as was the case with augmentations or with generative models, you have to think whether what you're going to be generating can hurt the actual thing that you're trying to learn. For instance, if what you're trying to learn is to detect people for a specific sensor, so maybe one of these specific boxes, perhaps using images that are so perfect because they didn't actually come from a sensor, even though these are modeled on sensors, they are not the real sensors, right? So there's going to be what we call a domain gap between the real images that you will be getting from your sensor and what is being simulated. So you need to think which part of all of this is your focus. Are you going to be training the full thing and then it makes sense to have a simulated world, or were you interested in say a perception system, and then perhaps that difference between what's real and what's artificial might hurt you. Okay, so just a quick recap. We've seen a few techniques that can help you either multiply the real data that you do have or generate completely new data that with different degrees of realism. Remember to think about whether the images that you're generating can somehow mess with what you're learning or not. So there's no golden solution that can solve the problem for you. But at least what you have now from this presentation is a list of tools that you can go out and use. All of them have Python APIs that you can use. And so all I can say now is have fun. And I hope to get a ton of questions, comments at the Q&A during the event. Otherwise, keep in touch and stay safe. Bye.